Good afternoon, everybody. It is 3 o'clock. This is Dan Geller from the Climate Learning Network. Welcome to our monthly webinar. Before we get started today, I have two announcements from the Climate Learning Network that I'm really happy about. The two things that we've been talking about doing for a long time have finally happened, and you can be a part of them. The first one is the Climate Literacy Certification. This is open to anyone at a land-grant university that's a member of e-extension. And if you don't know if you are, you can email me at dgeller@sref.info. We can figure that out. If you're not a member of e-extension, we can also get these modules to you, so let me know. But if you're interested and you are a part of e-extension, the easiest way to find it is to log on to campus.eextension.org and then search for climate literacy, and it will come up. You can also use this rather complicated bit.ly link to find it, but it's much easier if you just log on to the campus and locate it that way. This is an 8-module training course, and at the end you get a certificate. It's pretty straightforward. You can do it probably in about a week. Each module is about an hour, and there's a pre-test and a post-test. So we'd love to have your feedback on anyone who takes it, and we would love to have you take it. It's free, so again, if you have any questions about it, dgeller@sref.info or dgeller@uga.edu, and you can find me. Secondly, we have an upcoming online virtual conference. So this is in conjunction with the e-extension Climate Forests and Woodlands Community of Practice. And this is something we've dabbled in already. We did one with the Southeast Climate Hub and one with the Northeast Climate CAP on wheat. One of them we did 8 webinars a day for 2 days, so it was 16 webinars in a row. It was pretty intense. And the other one, we did one every Monday for 8 weeks in a row. That was for the wheat cap. And both of those formats worked really well. We're not quite sure what we're going to do yet, but we're taking a call for proposals right now. So if you're interested in this, anything regarding climate, forests, woodlands, we'll throw agriculture in there too, more than likely. So natural resources, anything about climate that you're doing with an extension bent will work for this. So if you're interested in this, you go to cfw.climatelearning.net, virtual conference, and you can register there. Again, if you're interested, email me, and I'll put my email up in the chat later so everybody can write me if they're interested in that. But this is a real fun way to get a conference on your CV. Your bosses probably won't realize that you really didn't go anywhere, so it'll work out really well for everybody. And honestly, this may be the wave of the future. We've had great luck with this, and it saves a lot on fossil fuels. So if we're doing a climate webinar or a climate conference, why not do it this way? So we'd love to have you all join us. And with that, I'm going to hand things over to Amy Crummon from Colorado State University. And I'm going to hand over control to Alan. And Amy, take it away. You can introduce everybody.
Fantastic. So thanks everybody for joining our webinar today on irrigation scheduling tools for improved water management and water use efficiency. It's my pleasure to be introducing 3 of our project team collaborators, Alan Nandales, Danny Rogers, and Jim Berdovsky. They are part of our large group of collaborators. There's about 70 people based in 6 Ogallala states at 9 different institutions. This CAP, this Coordinated Agriculture Project, was funded by USDA NIFA to bring people together to work across state lines, across disciplinary backgrounds, and we have a wide range of research that we're doing that covers everything from investigation into soil health under limited and dry land systems and crop rotations, alternative crops. We're looking at synthesizing and expanding knowledge, so relating to water use. That's everything from those agronomic systems to the economics and the social factors that drive decision-making around the water. We are also supporting, our project is helping to support the development and also is working to encourage greater adoption of successful tools and practices. So this could be pushing ahead on integrating things like drones and coupling them with VRI, to using soil sensors, and the other tools that we're going to be presenting today. The 3 folks presenting today have been working for a long time on the 3 tools that they're going to present. So we've got the WISE Scheduler. If you don't mind going to the next slide, Alan. We have 3 tools that are going to be presented today that existed prior to the funding for our project, which began 2 years ago, but they're constantly evolving and developing. So today we're going to get to take a tour of 3 of these tools. We've got the WISE Irrigation Scheduler, that's out of CSU, the CanSched Scheduler out of Kansas State University, and the DM tool from Texas A&M. And so with that, The last thing that I'll say before I turn over is that we're looking at the different ways in which providing the range of options and trying to communicate a lot about the range of things that people can do, and some of these things that they can do to manage their water, and consider the whole return on investment, the return on inputs used sometimes can be related to targeting water use. There's many different ways to target water use, and these three tools, which are not a very high cost addition to an operation, could be quite valuable. So with that, I'll turn it over to Alan.
Before we get started, I want to interject one thing. If you have any questions, please use that Q&A panel, and I see that Sonny H. already has. We'll be answering all questions at the end of the presentation. So just use that Q&A panel, and we'll get to them at the end. Thank you.
All right, thank you, Dan and Amy. So what I'd like to do for the next few minutes is to go over some concepts and terminologies that are common between or across irrigation schedulers, just to make sure that we are on the same page. So this first slide shows the concept of depth of water. And the depth of water is, you can imagine it as being the equivalent amount or height of water that exists in the root zone, which is represented in this illustration by DRZ. So the DRZ is really the reservoir of the plants for taking up water. And the water that we apply through the irrigation system or comes through rainfall is stored in this root zone. And towards the right, you can see if we theoretically separate out the three main components of the root zone, mainly the solid part, which is represented as depth of the solids. And then there's depth of water, which is the equivalent amount of water in that whole root zone. And then depth of air, which is the amount of the void space that is occupied by air. And so the concept of depth of water is really just determining how much equivalent depth, total amount of water in equivalent depth is inside this whole root zone. And so, for example, if we have a meter of root zone depth and we have, let's say, 0.25 meter of water, depth of water, that's equivalent to having a moisture content of 25% or 0.25. So there's just a slight lag in the response. Okay, there it is. So depth of water is estimated as the product of soil water content, volumetric. So this could be in the units, for example, in inch of water per inch of soil. And you multiply this soil water content by the total depth of the root zone, and what you get is the equivalent depth of water in that root zone. So another useful diagram is this conceptual bucket of plant available water. And so we can conceive of the soil, that root zone, being able to hold water between the upper limit of field capacity, represented by FC at the top, and then permanent wilting point, PWP, which is the bottom limit of that available water capacity. So the difference between field capacity and permanent wilting point, that's what we call as the available water capacity, or AWC. So this is what the plants can extract out of that root zone. But in terms of irrigation management, we do not allow the plants to extract all of this down, all the way down to wilting point, because the plants will be stressed by then. They would have experienced water stress. So we set management allowed depletion, which is represented by that red horizontal line, MAD. Typically for grain crops, for example, that's approximately halfway between field capacity and wilting point. Then what we do is we try to track this deficit, this D value, which is represented by this red portion of the bucket. And the deficit is the difference between the actual soil water content and the field capacity. So the deficit is what we use for irrigation management. It indicates the net amount of irrigation water that has to be applied. So if you track the deficit, then you already know the net irrigation requirement to get back to field capacity. Now, the deficit is just compared to this management allowed depletion, which can be converted to equivalent depth of water. And if the deficit is 0, then the soil water content is at field capacity, and you don't need to irrigate. While if the deficit goes below or past the MAD, then the assumption is that the water, the plants become stressed. So most of you have probably seen this diagram, which just shows the water balance components. So right there, drawn in or indicated in the root zone, is that current deficit. So that's what we want to track when we try to do irrigation scheduling, is we want to keep track of whether or not that deficit is 0, if the soil is at field capacity, or whether the deficit is going past the management allowed depletion, which indicates that the plants are stressed. So the deficit is really, the current deficit can be calculated by getting the previous deficit. So if, for example, if we do this on a daily basis, the previous deficit is from the previous day, and then you add the evapotranspiration, the crop ET, which is the water extracted by the crop, and then you subtract the precipitation, irrigation, and possibly capillary rise if you have a shallow water table contributing to the root zone. All those have negative values because they add water to the profile and reduce the deficit. While surface runoff, SRO, and deep percolation, the DP, add to the deficit because they are losses, water losses occurring from the applications. So the biggest portion of the water balance is usually the crop evapotranspiration, or what we call just ET. And crop ET in most irrigation schedulers are estimated using this equation, where first we estimate a reference crop evapotranspiration. So in the US, typically we use either a tall reference crop like alfalfa or a short reference crop like grass. And this reference ET is normally calculated using a theoretical equation. We call it the Penman-Monteith equation, but the assumptions are highlighted here in red, that this theoretical crop is uniform in surface, very dense, and it's 50 centimeters tall all the time if we're using the alfalfa reference, or 12 centimeters tall for grass. And it's never short of water, and it covers an expanse of at least 100 meters. So that's the assumption of the reference ET, and it's really just an equation that takes the variables of solar radiation, temperature, humidity, and wind speed that goes into this equation. So once we have the reference ET, we multiply it by a KC, or a crop coefficient, that scales up or down this reference ET based on the actual crop. So theoretically, we determine the crop coefficient by getting the ratio of actual crop ET and dividing it by the reference ET experimentally. So that's how crop coefficient curve is derived. And I'll show an example of that. And then finally, we multiply it with another coefficient called soil water stress factor. And this is a number that just goes from 0 to 1. 0 being full stress, so you'll see that if you multiply the whole equation by 0, the ET is 0. And 1 is no stress. So this is a photograph showing a good source of weather data. The weather source is important especially in calculating the reference ET, because the quality of the weather data affects the calculation of that crop ET. And so this is a good source where there's a surrounding grass field that's clipped and well watered, providing good representation of irrigated conditions. And then all the sensors, radiation, temperature, humidity, and wind speed are all mounted on that tripod that you see there. This is an example of a bad source of weather data where the surroundings are all dry. The temperature sensed by the sensors will be elevated, and probably also typically very low humidity because of the unirrigated conditions. So I would not recommend you use the data from this type of a weather station. Here's an example of a crop coefficient curve for corn. This was derived in southeast Colorado, but the diamond blue points are actual ratios of corn ET divided by the reference ET on a daily basis, and then the red, the black solid line is just a curve that we fit to make it smoother, and that curve is what we can use to estimate the growth of the plant. So you can see that 20 days after planting, the crop coefficient is still fairly low, around close to 0.1, and then it rapidly increases because of the growth of the canopy and the height of the plant. It plateaus to around 1 or a little slightly over 1 because of canopy closure, and then it drops again towards the end of the growing season, mainly caused by senescence or leaf die-off as the plant matures. So different irrigation schedulers use different types of crop coefficient curves. Again, the crop coefficient can be based off of a grass reference, or it can be based off of a tall reference, alfalfa. And so these are just examples of varied crop coefficients. The top curve is showing crop coefficients that are using an x-axis called growing degree days, which is the number of heat units accumulated by the crop over the growing season. And for example, CanSched uses actual days after planting, which can be translated into just an actual date. So you can see that at the bottom. And then the crop coefficient, the stress coefficient representing soil water is represented by this diagram, where the y-axis is the Ks from 0 to 1, and then the x-axis is shown here as depth of water. So when the depth of water is at field capacity, DFC, then the Ks is 1. And then the Ks remains 1 all the way until it gets to the management allowed depletion, or DMAD. After that, if the depth of water continues to be reduced going towards wilting point, there is a linear increase in the stress, and this Ks linearly goes or moves towards 0. So let me just spend a few minutes describing these concepts being built into an irrigation scheduler developed for Colorado called WISE. So this stands for the Water Irrigation Scheduler for Efficient Application. And you have the website there. The main page looks like this. And at the bottom of the page, there's a link to how to get started. We have some YouTube videos that show how to set up a field, for example. and start scheduling irrigations. So the WISE tool really has three main parts. And towards the left of this diagram is the client, where the user interacts with the app. So it's either on a mobile phone or a web client that is using any web browser on a computer. And in the middle there is the application, these virtual machines, which pop up once the user opens his or her user account and starts using the WISE app. It's like a model, an instance of the model for every user. So if you have 100 users, you have 100 virtual machines starting up on the server, modeling their own fields. And then towards the right, it's just showing all the components working in the background on the cloud, weather databases, also soils databases where we estimate the field capacity and wilting point to get that available water capacity. The weather data is primarily used to estimate the evapotranspiration of the crop. And then towards the top of these services are really the models, the hydrology models and the simple plant models that we use to estimate that daily water balance. So here is an example of an output from WISE. So the graph is showing you the x-axis as date, and then the y-axis is showing water, depth of water in inches. And the red curve there is showing the management allowed depletion. And the blue curve, which is like a sawtooth curve that goes up and down, that is the deficit, the soil water deficit in the root zone. And so you can see that this example, the deficit is being controlled. Irrigations are being applied, shown as those purple bars that show up whenever the deficit starts approaching the management allowed depletion. And the deficit, of course, turns zero when the soil moisture is at field capacity. So in this example, towards the middle of the growing season, you can see the irrigator is really applying irrigations regularly and not really letting the deficit go all the way down to the management allowed depletion. So in terms of an app, let me go through just a few screenshots of the app that we have. We have this for the iPhone as well as the Android platform. So the app is really meant to be used after the user sets up the field and starts the irrigation scheduler through a PC or a computer using a web browser. So once that field is set up, then when the person logs into the app, the fields that were set up using the web browser show up. And then once you click on a specific project, then the fields that are within that project show up. And then when you click on the project, then the water status is shown, just like the bucket, the simple bucket concept that we talked about earlier, where field capacity is shown, the wilting point is shown. On the right-hand side of the screen are the equivalent amounts of inches of water at wilting point and field capacity. The MAD is shown as a solid black bar, and then the red portion of that bucket diagram is showing the deficit. So really the user just looks at this app and just checks to see if that deficit is approaching that MAD. And the deficit is also given on the right hand of the screen, kind of in the middle. In this example, it's 1.35 inches of water deficit. And there's also some help for definitions, and also once the user decides on an amount of irrigation, he or she can input that as the gross irrigation amount in the app, and it is automatically sent to the server to update the water balance that's calculated. And you can even see the previous day's weather to look at the status of the weather. So we have been testing this WISE app over several years, and this is just an example showing some of the statistics that we've been using, comparing the estimated deficit from WISE to actual measured deficits using soil sampling outside the field. So this is an example from 2010 to 2012. I'd just like to point out right at the bottom of the table, just an average error, our root mean square error of around 16 millimeters of water. That's the difference between observed and calculated or estimated. And then right at the bottom corner, right corner is 13.6% error. So that's a typical error value that we see, which we think is good enough for irrigation management. And lastly, I'd just like to show you an example of a comparison we made with irrigation being managed by the producer, which shows up in the middle column right there. And the gross irrigation that he ended up applying was 20.1 inches. That's under his own typical management. And then the rightmost column is showing what would have been applied, 14.6 inches, which is significantly less than the 20 inches if the WISE recommendations were followed. So this is just an example that there is potential for water savings. So in this case, 27% savings in gross irrigation, and a 75% reduction in deep perk and surface runoff, which could also be saving chemicals, nutrients that may have been lost with the actual deep perk and surface runoff that may have occurred. So with that, I'll stop here and turn it over to Danny.
Very good, thank you, Alan. You know, I'm gonna tell you kind of the history of the CANSCAD program, and first I say it's CANSCAD. It's not the Kansas scheduler. It's you can schedule, but we obviously use the K from Kansas. But and Alan set it up perfectly with his description of the soil water balance, where we estimate the water use extraction by using ET as the estimate. And it still says I'm viewing. Do I have control yet? There we go. Well, it advanced. I thought I'd start with I started in the late 70s, and we wanted to do irrigation scheduling at the time. At the time in Kansas, nothing was metered, so we had a water conservation and utilization program promoting the use of water meters, knowing that pretty soon they would be required based upon the activities that were occurring at that time. And we were promoting soil-based irrigation scheduling using what were a common tool at that time is a gypsum block. You can see, though, from the hand-drawn graph there, it was a pretty tedious process where you'd have to go install the devices, you'd have to go read the devices, you'd have to plot them, and then make your decision. And still not getting activity here.
Hold on here. Let me see if it says you have it. Let's see. See if you can take over here. All right, you have control. I would click and then try to use your arrow.
Well, I'm afraid also it's going to advance about 7 times now.
Well, I can advance you from this end.
Just advance it for me then.
There you go.
And well, of course, now you can advance again now because, you know, the technology on saltwater based has improved a lot, because now you can have it sent to your palm and it plots it for you automatically. But it still has, I think, the advantage of the ET-based scheduling is that we're getting that atmospheric demand for the entire field. And just a picture showing it was actually working back then. Here I'm at a field day. But you can imagine the difficulty of promoting ET-based scheduling when you have to run out to the weather station, grab the data, come back, and we had a great, you know, new tool, the programmable TI-58 calculator, so we could actually calculate the ET reliably, and then we'd have to broadcast it over the radio or publish it in a weekly paper. So daily ET-based scheduling was kind of difficult. You go ahead and advance again. And but we started using it at our experiment stations. So here's a spreadsheet. It's actually just a notepad of hand calculations doing some of the original plot work that Freddie and I did starting in the late 70s and early 80s. Go ahead and advance. Of course, now that we have the some of these scheduling tools, that's all those calculations are handled automatically in a nice, neat little package, and either in and then plotted. Go ahead and advance. But all during this time, even though we had the limitation that you would have to hand calculate these simple things after you got the ET values, the hard part's the ET value. So we had bulletins on that. But finally, towards the late 80s, we started doing surveys and find out that, you know, the increasing number of PCs that were available to farmers. And so we actually put out our first version of CANSCAD as a Excel file. And it's essentially the same today. You go ahead and advance. You would, you know, you'd have to go through the different tabs to input the information that Alan described that you need for these programs: the soils, the crops, when they were planted, and you know, the other parameters that define that field characteristics. And then go ahead and advance. And then of course it plots it out on like the budget sheet in a table form or in a plot like I'm showing here. But the Excel program had a distinct disadvantage that it was one file, one field. So when you have farmers that have multiple fields, they didn't like that very well on the few that we did get to try using it. Go ahead and advance. So we actually put out the first version of CANSCAD that was compiled. Still, though, you would have to. I mean, you would once you set it up, then you could have multiple fields within that program, and it was much easier to handle, but still had a lot of limitations. But as you advance through, go ahead and next slide. You would see the fundamentals were still the same. We tried to carry the point and click capabilities from one program to another, so that it'd be a seamless adoption of the new program. And so there was a lot of buttons and drop-down menus, and then about the only data you'd have to enter would be your reference ET value itself. Go ahead and advance, and then you'd have your nice printout of your budget page and advance to that same chart that we saw earlier. Go ahead and advance. Then advance again. The next way we started distributing this was through a funded program at that time that we eventually called the Mobile Irrigation Lab, and advance. It was had two or three fundamentals. We were promoting ET-based irrigation scheduling, and we were doing that with hands-on irrigation scheduling training sessions, and we had other software also that we were developing as irrigation decision support software. But at that time, approximately 80% of our producers had PCs. I don't have data on this, but I would guess 90% of them didn't know what to do with them. And so when we'd come to these trainings sometimes, where we give these laptops and lay them out, one of the first steps we'd have to do with some of the guys is says, hold up a mouse and said, this is a mouse. This is what controls your computer. I mean, it was pretty basic. We don't do that anymore. Everything is, I mean, obviously we've come a long way since then, but the other aspect of that was that we were doing field evaluations of center pivot performance, which is the primary method of irrigation here in Kansas. And so we wanted to make sure that our systems, we're trying to promote to make sure our systems were operating properly and uniformly. go ahead and advance. And but at the same time, trying to promote this ET scheduling, we would set up a variety of, quite a number of cooperator fields. And what we would do is we'd modify strips within that pivot within the first couple spans so we wouldn't affect many acres, and set up, eventually we evolved to having 100%, 75%, and 50% of the producer application, and go ahead and advance. And this is data from 1999, one of the first years that we were doing this. And we're just going to look at site number 3. What the low bar is the dryland county yield for that field, county average compared for 99, compared to the yellow, which is the county average irrigated. And then the green is 50%, dark blue is 75%, and light blue is 100%. Now, what do you notice there? Almost all the yields were the same for those 3 things. Then 2 years later, advance for this particular producer. You'll hopefully it's shown. I got the bottom cut off on mine. It's the third one. It's the last one, the far right. You'll see the county average and dryland for that year. But you'll notice that the green bar, 50%, there was a big yield suppression, and in 75% there's yields depression, and then 100% looked pretty good. At least it was better than the county average. And now that same producer was complaining to us that we're causing him yield loss in those strips out there. Now they were about a half an acre. But we would say, well, look, now at least you know that you're approximately applying the right amount of water. We actually started out with 75%, 100, and 125%, but man, they were all overwatering so much that we went the other way. Go ahead and advance. And so that's just actually, to start this program, we couldn't get them to use the weather station data. We had to put atmometers at each one of their fields. And one of the requirements was they'd have to read the atmometer and go get the ET data from the weather station. And about halfway through the first year, when they started doing that, they were complaining, hey, why do we have to go out to the field and read that atmometer? We can get it off the weather station. But that was the point that we were trying to show them, that the weather station doesn't have to be in their own field to have good data. Well, as we evolved along, then we obviously computer capabilities gotten better, and then we introduced the CANSCAD 2, which allowed them to group their fields together more, to manage and reduce the number of entries, so that once your ET data entered into one field, it would be entered in all the fields associated with that station, and upgrades like that. And then we up until this time, we'd been distributing it by CDs, because the web access in western Kansas was spotty, unreliable, and all the issues associated with new technology. But after at the introduction, about the time of introduction of CANSCAD 2, go ahead and advance, we started delivering the programs via the web delivery. And so there's the screenshot of the first MIL website. It's been upgraded and moved several times since then. We continue to use, go ahead and advance, we continue to use the web as our major delivery point, and have converting all our CANSCAD programs to web delivery. So CANSCAD 3 is an online or a web-based program. But it follows the fundamentals of the previous versions. And go ahead and advance. We use it at all our, most of our research plots that have a water function are ET-based schedules, so that everyone knows when they hear a presentation on tour at a field day, they know how it was presented or how that was calculated. We also have a number of water technology farms to promote new technologies, irrigation technologies, and we use CANSCAD to provide the water balance on that. And so this is at one of the tech farms near Larned. We go ahead and advance, and we always compare that to the soil-based measurements there, and most of the time they match up really, really good. We actually said it was wetter or had more withdrawal by CANSCAD, which would be conservative in this particular case, because those fields were actually it was very, very dry, and the crops weren't. We probably didn't have enough. Actually, were drier than what their soil. They were dry, and but we don't dry it down so much. Anyway, the next slide shows that we are. Oops, I guess I got one ahead of myself. Stay right there. Stay right there. We put in some new features into the CanSched 3, but we're also working on the smartphone interface. Go ahead and advance, and one more time. And just like Alan had showed on his, we think that's to really get us over the hump. We need to have those programs delivered to their palm of their hand, and we're also adding in some of the features they want, which would be like a notes section, so they can put in other information about that field and then be stored at the residual program. So one final slide then is that you've seen the evolution of CanSched, and I really feel like we went from the horse and buggy to on the verge of having some really nice programs, and we're still working on adoption. Almost every irrigated farmer in Kansas by survey says they use crop consultants, which all provide to them as a baseline information an ET-based schedule. But industry is also promoting soil-based scheduling, and so we have both methods running side by side, which I think is good because it's complementary. As long as the data matches up, then one's based on atmosphere, one's based on soil, and if they match up, you should know that you're on target with your schedule. And we think it will be also very complementary as we move to some of the aerial-based, imagery, whether it's temperature-based or frequency or whatever color. Anyway, that wraps it up for me. I'll hand it off now to Jim.
Jim, you should have control. You can try it if you want. It's not wanting to work today, is it?
It is not going to work.
All right, I'll take over. I'll intervene. There we go.
Okay, very good. Well, thank you, Danny and Alan, for setting this up. DM stands for Dashboard for Irrigation Efficiency Management. It's a product of Texas A&M AgriLife Research and Extension, as well as the Texas Center for Applied Technology there in College Station. And next. DM focuses on cotton in the Texas High Plains. Cotton is a crop that is grown widely, several million acres in this region. It's a little bit different than other crops in the fact that it's a perennial, and the management of that is a little bit different. The other point that I want to make in terms of DM, we're focusing DM on water availability, both the irrigation as well as rainfall. We have very limited irrigation capacity in our region. We're also within irrigation districts which can limit the volume of water that's available within a certain time period. So placement of irrigation amounts in certain times becomes critical. Next. The other focus point is irrigation characteristics. We have a high evaporative rate in our area, particularly in the springtime. We have different irrigation delivery systems, spray systems which wet the entire soil surface, as well as subsurface drip. Several 100,000 acres of subsurface drip where there's very limited amount of evaporation losses. And when you're limited on pumping capacity, those losses are very significant. And then there's the other inputs into DM. Next. What I'd like to start off by is talk a little bit about a field test that was conducted a few years back. There's 27 different irrigation regimes looking at different irrigation capacities within different time segments across the growing season. And this is just a field shot of this one treatment, this LMM treatment. And we're going to compare it to a more traditional treatment. Next slide. this MMM treatment. Next. All right, the LMM, this treatment was one where we started irrigation later in the growing season. It was mid-July, and this particular plot, the pumping capacity was relatively low. It's less than an inch per week. Next, versus the traditional treatment where we started earlier in the year, or in June, again, same pumping capacity. Next, the difference between those two in terms of water availability or water put on those crops was 3 inches in 2013. Next, and what we were looking for was an increase in yield going from the tradition to the from the low or late start to the early start. The gain from that 3 inches was only 18 pounds of lint per acre. Next, and if you look at that test, those two treatments across 4 years, which included 2011, which was extremely dry year, that average of 2.7 inches of water per year only netted about 10 pounds of lint per acre each of those years. Next. So what we're trying to do is capture the information that contained within this series of experiments in a web-based solutions, and DM is the result. This is the what you'd see is on startup of our web page. There are a number of buttons and charts there. We'll go through a few of those. This first one, you can input the field name, characterize a field and scenario. Next, a weather station selection. We currently use the West Texas Mesonet as the source of our weather data. Next, there are editors to change various things that need to be changed as the crop season goes along. Next, model outputs. There are dynamic outputs that you can see, numeric outputs that you can see immediately as things change. Next, there's a component area on the left-hand side. Next, within that component area, next, there's the type of data that Alan mentioned earlier, soils. Next, crop. Next, and irrigation data. Next, the main output is a soil water chart, and you've seen these in a little bit different format of the previous two speakers. Next, the y-axis, of course, represents the plant available water. It's not all the water in the profile, but just the plant available water. Next, across the y is time. Now, one of the differences that what DM does is look at time across the entire growing season. So we have data, current data up to a point as of today, and then from today forward, we're using historic data from that weather site that was selected by the user for that field. So we're looking at the entire growing season and coming up with soil water contents and projected yields based on that each time we look at DM. Next, we got to use a target soil water content, which is a function of the crop and the environment, the weather for that crop for that particular year or projected year. Next, soil water, estimated soil water content, soil water balance, as Alan described earlier. Next, the soil water content where transpiration is reduced. Next, rainfall, of course, is plotted. Next, as well as irrigation. Next. Okay, an example. Assume that we were sitting on August the 1st. Next, we would have our current year's data for that year up to August 1st, and we'd have the soil water content and soil water balance based on real data, irrigations, and rainfall. Next, the rest of that year would be based on historical weather data that the user selected on that weather site, on that weather station. Now, he can pick a dry year or a group of dry years, wet years, El Nino years, he could pick last year's data and project what might occur in the future. Next. Now, what DM does is look at the soil water content, project the yield based on the field data that we acquired in the previous experiments. It reschedules the remaining irrigation from that point on to optimize yield. So it rescheduled multiple times to optimize yield. Okay, next. Okay, this is an example where we're going to toggle some switches and look at what ifs, and we're going to change irrigation systems because it's fairly dynamic. Next, we're going to assume this is the 2018 growing season. Next, we're going to use weather from the Texas Tech Mesonet site in Plainview. We're going to use average future data. Next, our irrigation capacity is going to be set at 0.2 inches per day. We're not going to set a volume limit. We're just going to set the pumping capacity limit. Next, we're going to use an irrigation system called LEPA, Low Energy Precision Application. This is a system that would wet up only about 1/3 of the soil surface. Next, when we hit the execute button, we will see that we have a yield score of about 1,500 pounds of lint per acre. Next. Okay, now we're going to change to a low elevation spray, a LISA type system, which would wet the entire soil surface. Next, I want you to notice the soil water content line. This is being projected. Next. All right, the line dropped. When we executed the DM, the line dropped. Next. We'll also see that the yield score dropped, and I don't have it in here, don't have it highlighted, but we'll also see that the water content or the amount of irrigation for that year increased. Next. All right, we're going to look at subsurface drip irrigation where there's very little soil surface evaporation. Next. Here again, notice the soil water line. Next. We'll see the soil water line jumps up. It hits the target water content. Our yield goes back up. Also, the amount of water that we applied during that growing season was less than either of those other two. And the whole point of this demonstration is the fact that you can go in and look at current data up to the current date and then start projecting and playing what if, and then make decisions on what you might do differently in the next few months, if you have that time in the future. Next. Several outputs. This is an output that could be either be printed or seen on the website. Next. It has the basic information. Next. Weather station. Next. And then an irrigation schedule. Next. We also have a mobile app. Next. And it utilizes the data from the web server or the web client to populate information on the mobile app. Next. Access is available through dm.tmu.edu, and you can contact Dr. Porter or myself if you're interested in more information. You can access that site, get a password. We have access to user guides and a help desk via email. Next. I also wanted to mention the fact that there are several other soil water balance tools available. This is a few of those that I'm familiar with. There are differences in these. There are different sources of data. Different crops in some cases, different crop coefficients, different levels of complexity. And my only point here is that if a tool doesn't work the way you like it, or you stumble with it, or you see something different, there are other tools available, and not to throw in the towel when you see something that you don't like. Inform the person that has developed the tool, but keep looking. Next. I'd also like to acknowledge on behalf of my co-speakers the support from all the agencies that we get funding from to support our programs, federal, state, and in many cases, commodity organizations. Next. Okay, Alan, I think it's back to you.
Okay, thanks, Jim. So this is our last slide, just kind of summarizing the talk. Certain benefits of irrigation scheduling were probably obvious from the three presentations, but it's really at the bottom line is improved irrigation application efficiency. So once you're tracking the soil water content using an irrigation scheduler, then you can prevent over irrigation, especially during wet years, or prevent under irrigation and too much water stress during dry years, just by knowing it, or having a good idea of where your soil water content is. And because of that, then you could also make use more effective precipitation, especially when there is rainfall in the forecast. You can leave some room in the root zone for storing that extra precipitation, and you don't have to refill the root zone all the way up to field capacity, for example, so that you have room to store more rainfall. So hopefully this yield, this does lead to better yields, and possibly just by not running the irrigation system all the time, but basing it off of the irrigation scheduler's recommendations, you could also save energy and labor costs from reducing the number of irrigations. And environmentally, you could reduce the nutrient and chemical losses. And the nice thing about these irrigation schedulers is once you're done with the growing season, you have a record of your water use and your management. And you can go back to it again and again. And also benefits in terms of soil and water conservation. So I'd just like to point out a few limitations or caution when using these tools. So for example, the output you get from these tools will really depend on the inputs that you take, that you put into it, like weather data, how accurate is the soils data where you used to estimate the soil water holding capacity, and also these coefficients that are really based off of some experimental data, hopefully taken locally. And it's a good idea to also take a look at the estimated soil water contents from these schedulers, and every now and then compare them to actual observations or measurements from the actual field. These tools do not capture many of the natural hazards that occur in real fields, like hail or diseases and so forth. So in a way, just like I think it was Danny who was showing that, yeah, that sometimes the tools can overestimate evapotranspiration because it doesn't capture these reductions in the ET caused by damage, for example, to the canopy. And so, sometimes there are still issues with cloud or internet connectivity, but hopefully that will be resolved as we move forward and improve our technology. And that's it. We will now take questions.
Great. So yeah, please put your questions in the Q&A panel. We only have one right now, so if you want to ask something, please get in there. I did answer one by text. Someone had asked what the handle is for the Climate Learning Network who presents this. It's @ClimateLN, and I put that in the responses on the Q&A. The only question we have is, will this PowerPoint presentation be available for download? Do you mind if I put this up when we archive this webinar? Is that okay?
That's fine with me.
That's okay.
Great, yeah, so I will archive this on climatewebinars.net, so you'll have the video review and the actual presentation will be there as well. We do have a question from Aperturs. Is the irrigation start date entered in each tool?
Yes, it's entered in DIM.
Yes, and for Cascade.
Yep, the same in WISE.
Great, and that was from Andrew Peterson. He has a handle there. Okay, we have another question. What crops can these be used for? And could you also ask them what the tools costs?
CanScad is primarily directed for summer-grown grain crops. We do have people who use it for wheat, but we treat the fall and the spring, the two growing seasons, as independent crops. Just makes it easier for us, and it's a free tool at this point.
Yeah, what WISE is the same. It's also a free tool, and in addition to grain crops, we also have more of the common horticultural crops, potatoes. There's also sugar beets, and I think this is true for all the irrigation schedulers. We're all adding more crops as we get more data.
Yeah, I should say that, yeah, it's true. We only have certain crops programmed in. If someone asked me for it, we could give them those coefficients, but we don't have near as the horticultural crops that Colorado has.
We're currently using, in Texas, we're using crop functions for cotton and grain sorghum, but we're trying to add additional crops as data is available.
And see, that's a good point from Jim. We don't have any research on cotton in Kansas, but we're starting to grow a little bit on the southern edge. So if I get a cotton question, I refer them to the Texas program, because it has, I mean, obviously it's targeted towards cotton.
Great. We have another question that asks, are you familiar with FarmBeats technology for monitoring? That's FarmBeats, FarmBeats.
I am not.
I am not either. No.
Yeah, maybe the asker can explain a little more.
Yeah, but I think so. Just based off of what I know, there are private companies offering very similar capabilities for irrigation scheduling, and even the vendors of the irrigation systems themselves have proprietary systems. And so there are a lot of developments in this area going in parallel. Yeah, so sometimes almost it looks like they're competing against each other. Each state also has probably an irrigation scheduler, but I think the ones that we presented would be good starting points for just getting your hands-on experience, trying to track the soil water content and not having to pay for it. And then once you gain that experience, then you can move on to more advanced tools, just like what's offered by the private companies.
So Sonny put the link to that FarmBeats up in the Q&A panel if anyone wants to access that. And then we also had a statement that in British Columbia, the calculator is at the URL here. So there's one for British Columbia. You can access that by clicking on the Q&A panel, the Q&A button on your interface, and it will bring those up. And it looks like those are all the questions we have, which is great because it's 4:03 p.m. Eastern time. So we're done with this webinar. So that worked out perfect. I'd like to thank everybody for joining us. We'll have another webinar next month. Amy, do you want to talk about that one a little bit? I think you're muted. Let's see.
There we are. Sorry, I was trying to find my unmute button. Yes, thanks. So our project, the Ogallala Water CAP, is going to be on again next month. That's going to be Tim Shaver, and he's going to be talking about soil and water and nitrogen use efficiency research that he is doing. So he's from the University of Nebraska at Lincoln. And yes, we'll be back with you guys next month. And I think the date for that is it's June. Remind me again, Dan. It's
Let's take a look here. So I'm right.
Yeah, me too.
I can't. I have so many windows up. I can't get at it.
Yeah, it's gonna be.
It's the second.
Yeah.
It's the second Thursday. Like this one was. I think it's June 7th. Yep.
Yeah, June 7th at the same time. So 1 p.m. Mountain, 2 p.m. Central, 3 p.m. Eastern.
Great. With that, we're going to sign off. Again, the Climate Literacy Certification and the call for presentations for our CFW Climate Forest Woodlands Virtual Conference are both live right now. If you need any help with either of those or miss these URLs, just write me at dgeller@uga.edu. And with that, we're signing off for the Climate Learning Network. See you next month.
Thank you.
Hi, everybody.
Thanks to our speakers. And thanks for setting this up, Amy.
Thanks, Dan. See you next time.